All right, how's it going, everybody? We are here on Wednesday of week 9. We're going to talk a little bit about probability here today. Some of you guys might have noticed, maybe we should just mention to get started here. If you guys were here trying to watch the live lecture yesterday, I've been having I know I've said this to you guys a bunch of times already, but I've been having a bunch of computer issues here that are preventing me from doing a lot of different things. Grading is one of the things that's going infinitely slow for me because of my computer situation. I've been having some keyboard issues. I've been having some internet issues here. Those are why I couldn't do things, why I had to bump Monday. And then yesterday afternoon, I had connectivity issues and I couldn't manage to live stream this for some reason. But I was still able to make the video so that it is posted there. But I don't know why I couldn't connect yesterday to stream this live. So I guess that's fixed now. I don't really know what happened, but I can at least tell you guys I ordered a new computer last night. So hopefully I'm going to just not have any technology problems for the rest of the semester starting about a week from now, but that is to be determined, obviously. So let's go ahead and pick it up with our probability topic here. While this is one of my favorite topics, I've been telling you guys that for weeks. I'm not going to go too crazy and get into too much depth with this right here. There's a million things that we kind of could talk about, and what I just want to do is to give you this strong sense that probability and statistics depend incredibly heavily on calculus for all meaningful computations that happen. Um, to the end of, you can see my sort of joke up here at the top of the screen. The subtitle of today's talk is Why is it so hard for Tony to teach introductory statistics and calculus 2 in the same semester? And that's because all of the things that I want to be telling my stat students are calculus things, except none of my stat students know calculus, and that makes things very difficult for me. So today we're going to talk about how do we perform the associated computations that are related with some probability ideas here. And we're going to start with some not probability. And that's kind of the same thing as how in every other lecture we start with doing things like Riemann sums and we upgrade them to integrals, stuff like that. We're going to kind of follow that exact same trend here in this little video right here. So let's go ahead and kind of get started here. So what we want to do is we want to define a probability distribution function, and we want to see how it relates to a very simple case here, and we'll kind of immediately get into upgrading our thoughts into integral thoughts rather than sort of the more basic computations that I have my introductory stat students do. So another thing that's going to happen here today is I'm going to throw a bunch of stats vocab at you guys. This isn't necessarily like a list of vocabulary I need you to study, but like these are some things that you should be okay with these words being thrown out there, right? So given an event A, it's first things first. It's pretty typical in probability and statistics to label your events of interest as capital letters, right? So an event A, we might want to know all the possible outcomes and their associated probabilities, right? So all possible outcomes of an event is what we call the sample space. It's everything that could possibly happen. Then we also are probably interested in the associated probabilities with each of those things. So what we kind of know, we're going to look at a really simple example here, but I'll verbalize some slightly more complex examples here. Um, and a very important distinction that I'm going to be making here is that the discrete examples are easy for my statistics students to do. The continuous examples get into the realm of where we need calculus to help us out a little bit, and that's where we need to use technology in the stats class, but where we can just use integration in this class here. So we're going to look at the most basic and boring example that there possibly is of a probability distribution function, rolling a six-sided die. I know that I could pick something that's more exciting, but there's no reason to do so right here. This is going to be a perfect representation of exactly the thoughts that we need to be thinking here. So when we're talking about rolling a six-sided die, the reason I picked this is because everybody knows what it's like to roll a six-sided die. You know that there's six values on it, 1 through 6. So here, what we're saying is that the x value is the outcome of rolling the die. We're defining the variable x to be the roll of a single die. X is the outcome of one roll of one six-sided die. So here's the definition of my variable x. And so this row is the x values. This is the sample space right here. And by the way, I'm emphasizing the sample space because we're going to get a different word for this when we get to our continuous stuff here in a minute, and that one's going to matter a little bit more to us here. So this is our sample space here, and these are our probabilities. And a very important thing to notice that's associated with any probability distribution. So a probability distribution needs to reference all possible outcomes. If all outcomes have been referenced, then that must cover 100% of all possible outcomes, and therefore the things that we're going to see here is that In any probability distribution function, or so PDF, a probability distribution function, this is our function that's going to define, or not necessarily function, it's our description of all possible outcomes and their associated probabilities. In a continuous setting, this will often be given as a function, like an f of x function, but in discrete settings, it's a lot more typical for us to just give a table, right? So this is a discrete PDF as a table. Right. It's a table because we're just making a list. It's a discrete probability distribution function because our outcomes are discretely separated there, right? There's 6 possible outcomes. There's only 6 things, a finite number. I can measure the distance between them. So the two things that need to be true of every probability distribution function, every PDF, is one, all probabilities only even make sense to be between 0 and 1, right? There's no such thing as there being a negative 10% chance of something occurring, and there's no such thing as 110% chance of something occurring. I want to make a real quick distinction, though, if we're thinking about how probabilities work. It does make sense for me to have 150% of the money that I had last month. That means that I have 50% more money than I had last month. That makes sense. It does make sense in life to talk about percentages that are larger than 100. It does not in life make sense to talk about probabilities that are larger than 100. Both of them are listed as percentages or as decimals. But there's a little distinction there, right? So again, I can have 150% of the money that I used to have. That means I have 50% more money. That's not a weird statement. On the other hand, it does not make sense for me to say there's a 150% chance of some event occurring, right? So the probability of an event occurring has to be between 0 and 1. So we generally phrase this as just saying 0 is less than or equal to p sub I is less than or equal to 1. P sub I being in the ith probability. This says for any of the probabilities out of the n probabilities, if you pick the ith one, it needs to be between 0 and 1 right there. So this is just our general statement of all the individual probabilities are between 0 and 1. The other thing that's really, really important here, in fact, even a little bit more important for us than that kind of more obvious statement right there, is that if you are really fully describing a probability distribution, then you have described all possible outcomes. And therefore, since it's everything that could happen, the probabilities of all possible outcomes should all sum to 1. It really matters that all probabilities sum to be exactly 1. If they add to more than 1, then you've somehow double described some of your events. If they add to less than 1, then it's not a full probability distribution. You haven't described some of the possible outcomes if it sums to less than 1. So a very important feature of PDFs, I mean, it's really just these two things right here. But in my mind, sort of the more important one is ensuring that the sum of your probabilities goes to 1. So it should be that the sum of the p sub i's is equal to 1. There's my sort of math notation for this. So let's get into some actual computations here. This computation is going to be not super exciting, but it's a little bit weirder than I guess what we typically think of when we see these things. So what is the expected value of the roll of one die? This says if I were to ask you to roll one die, on average, what do you expect that roll to be? All right, so this is an average question right here. It's phrased as expected value in a probability setting. What do we expect the outcome of the roll of one die to be? Now, what we know is that these die rolls are uniformly distributed. For a distribution to be uniform means for all outcomes have the equal likelihood of occurring. So here, all outcomes 1 through 6 have an equal likelihood, a 1/6 chance of occurring. So it's a little bit weird for us to talk about expected value in this case because I don't expect any one roll any more than any other roll. So sometimes it's a lot easier for us to think about expected value as to say, if you were to roll a die many, 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 many times, what would your average roll be? And here's the way that I'm going to go ahead and think about this one for myself now. I'm going to formulate my computation in one way, but it's really so that I can rephrase it to look a different way. That's going to be the more helpful way for me. What I'm going to do for myself here is I'm just going to say, let's pretend that we roll 60 dice. What spread of outcomes do we expect? All right, so here's the thoughts I'm thinking. when I want to find this expected roll of one die, it's weird to think about just one die because there is an equally likelihood of all six outcomes. And so it's weird for me to gauge what I think is on average the most likely thing to see out there. So what I'm going to do is I'm going to give myself a hypothetical simulation here. In my mind, I'm going to simulate the act of rolling 60 dice. I'm going to think about what I expect the most likely distribution of results to be for those 60 dice. And since I'm looking for an average or expected value, I'm going to divide by the number of dice that I rolled. And so here's what I think I should be getting if I were to perform this hypothetical mental experiment right here. What I think I should be getting is I should be getting an equal number of each of the 60 rolls, right? So this says to me, I expect to get 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, 10 sixes out of the 60 total rolls out there. That would, I think, be my most likely event to experience right there. Now, this probability, I honestly think it would be weird if we got exactly those numbers right there. But that is, I think, our expectations based on the probability distribution that's been given. So I think that I'm going to see 10 copies. Hold on, let me. Yeah, okay. I'm doing a weird. What I was just trying to figure out in my head right there is if I wanted to put my parentheses around the 10 or around the 1, which is a really stupid thing to wonder about since the multiplication is indicated either way. But as I said a second ago, I'm trying to set us up so that this computation can be rephrased to look differently, so that we see an easier way to go about computing this than the way I'm going to do it right now. So I'm going to say what I'm expecting if we roll the die 60 times is 10 copies of a 1 plus 10 copies of a 2. Remember, we're looking for the average value. So I'm adding up all the values and dividing by the number of rolls. I'm expecting 10 copies of a 3. I'm expecting 10 copies of 4. I'm expecting 10 copies of 5. And I'm expecting 10 copies of 6. So that's the sum of all of values divided by the number of rolls should give us the average value per roll. Now, here's the thing that I'm kind of noticing out of this computation when I set it up this way. I'm totally happy with what I've computed here. This is the total value divided by number of rolls, gives us the average value per roll. But what I'm kind of noticing here is it might actually look a little bit nicer for me to decompose this into lots of small fractions right here. The reason I'm saying that is because I see, for example, 10 and 60 might make a nice fraction. And that's going to happen in every single one of these cases right here. So I don't need to do this simplification at all. I could just directly going, so pardon Reed, you're asking what's the probability of actually seeing the tens of each of them right there? We could compute that. That would be honestly a pretty difficult computation to perform right there, surprisingly. But it could be done, and we've got some distributions that help us do this. This is very much a hypothetical. What do I think is the most likely thing? Because I'm trying to come up with what do I expect to see and what we should expect to see. Because you're right, there is a probability that we're going to roll 60 ones in a row. In fact, that probability is much, much, much easier for us to compute than the other ones. If we're going to roll 60 ones in a row, then that would mean that we'd want to get a 1/6 chance 60 times. So there's going to be a crazy, crazy, crazy small probability of rolling that all 61s. There's our probability of 61s right there. And as you can see, that is an insanely small probability of that occurring right there. I will tell you guys some stupid, funny probability stories here at the end of this one right here. But again, right now we're trying to come up with what do we think that we should expect to get, not actually what are we going to get and with what probability are we going to get it right here. So this is an expected sort of a hypothetical scenario right here. So what I want to do is I want to simplify each of the 6 terms in my sum with their division by 60. And what I'm seeing is I can represent this as 10 over 60 is the same as 1 over 6 times 1. Plus a 1/6 times 2, plus a 1/6 times 3, plus a 1/6 times 4, plus a 1/6 times 5, plus a 1/6 times 6. And so what I want to do, the reason I usually write this both ways is because I feel like people are in general agreement that if you add all the values and divide by the number of rolls, you're going to get the average value per roll. So people are generally pretty okay with this as my formulation of our expected value and average value per roll. But what's more important for us to see is that when we do a little bit of algebraic simplification of that fraction, what we're seeing is this is just the probability of rolling a 1 times the value of getting a 1. The probability of a 2 times the value 2. Probability of 3 times the value of 3. It looks like what we're doing is we're adding up all of the individual probabilities of the event times the value of the event. And we're summing up all those guys right there. That's going to be really important for us here. So the question is, what do we actually get when we do this? Well, I can see what we're going to get out of this fraction here. It looks like a 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. And if I add all these up, 1 and 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. And I can reduce this a little. And that's weird. I just got a 7 over 2, and that is a decimal is 3.5. So in what way does this agree, and in what way does this disagree with what we think of for expected value of the roll of one die? The obviously weird thing going on here is it's not possible to ever roll a 3.5 on a die. But what I am thinking to myself is that if I were to roll this die many, many, many times, the average roll over many rolls is going to be a 3.5. So this isn't an expectation of a roll, but this is saying what number is going to be sort of the closest to all of your rolls. And 3.5 is going to be the one that's closest to all of our rolls. If you were to think it's going to be 3, then 6 is actually 3 steps away from 3, whereas 1 is only 2 steps away from 3. So we're not quite in the middle of all of our possible values here. What this is this is just a weighted average, but even in this case, the weights were all equal at 1/6 because there's an equal probability of all of them occurring out there, right? So the weird thing about this is it's not actually possible to roll a 3.5, but it does make sense that if you were to roll a die many, 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 many times, your average roll would be a 3.5. Because you can just see it right here. I mean, 3.5 is sort of what sits at the dead center of this distribution because 1/2 of the results are to the right of it and 1/2 of the results are to the left of it right there when you're at 3.5, right? So the strange thing about expected value is that expected value doesn't ever actually have to be a member of the sample space. Remember that our sample space in this case is 1, 2, 3, 4, 5, 6. We just found that the expected value is not one of the members of the sample space, but it does make sense that it's what we consider our average possible output to be. So when we're computing expected value, we might get some slightly weird answers right there that aren't in the sample space, but they're still representative of what do you expect to happen on average over many, many rolls out here. So the important thing that happened here is I see this sum right here. And so I do want to kind of write this sum out for what it actually is right here. It looks like what this is, very importantly, is this is the sum of, and what's first in each of the terms in the sum, it's the ith probability, and what's second in the sum is the ith value. Okay. And this is going to help us form a calculus statement coming up here in a second. Yeah, I'm going to rephrase this ever so slightly right here. I typically think of this, for example, as my like x sub I column. This is like, x sub 2, and I think of this as like p sub 2 right there. But it might be slightly more appropriate for us to use this probability notation. This is the probability of the event x occurring. So the probability of rolling a 2 is 1/6, stuff like that. So it might be that we want to kind of slightly rephrase this as the sum of p of x sub I, the probability that we see the outcome x sub I, times that value itself, x sub I. So the x sub I in each case is the 1, 2, 3, 4, 5, 6. The probability that we'll see x sub I was the 1/6, 1/6, 1/6, 1/6, 1/6 out there, right? So this is a really good statement for our expected value of any discrete random variable. In this case, our variable is discrete because rolling a die means there are only 6 possible outcomes. Let's see how this changes if we make this a continuous variable instead of a discrete variable, and we will upgrade our expected value computation to be that of something that has an infinite number of possibilities. So the point here is, where's the calculus? Hopefully you're starting to feel out that anytime we see a summation that looks like that, there is a continuous analog that is represented by an integral. So I'm going to change this problem ever so slightly. Now, instead of rolling a die where there is a discrete 1, 2, 3, 4, 5, 6 outcomes, we're instead going to say, let's write a computer program that randomly outputs any value between 1 and 6 with equal probability, right? So it's equally likely that any number between 1 and 6 is outputted. And what I want to know is, what is the expected value of the output of this computer program? So here's what I'm going to do to help myself compute this. A couple things here. One, I'm going to tell you about how we indicate our distribution here. If x is the outcome from the program, output of program, then we would notate this probability distribution by saying x, the random variable x, is distributed, using a tilde right there, is distributed according to the uniform distribution. And the uniform distribution always takes in a lower bound and an upper bound. Here we'd say x is, typically this is shorthanded, by the way, as unif. And in our case, the lowest possible value is a 1. The highest possible value is a 6. So this is our situation here. We are asking, what is the expected value of x when x is distributed according to the uniform distribution from 1 to 6? It's our fancy notational way of saying a not very complicated problem here. Now, in a uniform distribution, all outcomes are equally likely. And what this tells me is that the graph of my PDF is a flat line. Right. What I'm saying by that is if I want to graph the probability distribution function, the probability of any event is the same as any other event. So if x is my event on the x-axis and the height is the probability of the event, all my probabilities are the same. So I should be seeing just a flat function right here. It's going to be a very, very easy function for us to describe. All right. So what I'm going to do to graph this then is I'm going to graph from 1 to 6. I know that I should be experiencing this as my probability distribution function right there. That is the PDF associated with the variable x right there. Put those little dashed lines right there just to indicate that our probability immediately drops off to 0, right? There's a 0 probability that we're going to see something less than 1 or bigger than 6. So a couple things I want to know here now are this. If I am going to compute an expected value, one thing I know is I'm going to need to alter my summation formula to represent something where there are an infinite number of possible x values that we can take on, because there is an infinite number of possibilities out here. The other thing that I need to know is, what is this probability? What height are we actually sitting at here on this graph? Right? What is that height of that bar right there is not directly clear to me. So here's what I know. What is the height of this bar? Well, what I know is that since the sum of all probabilities needs to equal 1, what I'm seeing here is that the probability has to be equal to this area that's associated with what's going on underneath the curve right here. We're accumulating area in the same way that we accumulate probability. So our area under the curve must be equal to 1. Right? Fortunately for us, this is a rectangle. I can see that my width here is b minus a equals 5 for my width. So if the area is, width times height, I know that my area must be equal to 1. I know that my width is 5, and therefore my height is going to be 1/5. And that's actually really weird to me, because I feel like I generally expect fractions like 1/6 to be associated with rolling a die that has 6 sides out there. But technically, the width of this interval is only 5 units wide, and so therefore the height has to be 1/5 units tall, so that the area underneath the entire curve is 1. The sum of the probabilities is 1. What I want to do is I want to compute this expected value, right? So in our discrete setting, we said that our expected value is equal to the sum of the probability of x sub I times x sub I itself. So all we're going to do in our continuous case right here is just upgrade this to be an integral so that we get all of the probabilities times x of all of the x values from 1 to 6. And I'll just call it f of x right here times x dx. Right? So what we're going to do is we're going to say across all the x values of interest, we're going to do from 1 to 6. f of x is the same as p of x sub I, right? That's just our probability distribution function, f of x, or p of x, times the x value that's associated with that guy right there. So we're just, in a sense, upgrading this to be an integral computation now. And so I'm going to do exactly that. I'm going to get my expected value is going to be the integral from 1 to 6 of x times f of x dx. What is f of x in this case? For our uniform distribution, we have a very, very, very simple curve that we're describing. This is the curve that is my probability distribution function. And we can see that this is just literally the equation y equals 1/5. There's nothing, this is like the lamest probability distribution function in history. It's a horizontal line right there. Its equation is literally y equals 1/5. So it looks like our computation here is from 1 to 6. We're going to get x times 1/5, just the constant dx. So that's really just 1/5 times the integral from 1 to 6 of x dx. And so we can easily compute this guy. This is 1/5 times, this is 1/2 x squared, evaluated from x equals 1 to x equals 6. And to evaluate this guy here, pretty easy here. It looks like this should just be 1/10 times 6 squared minus 1 squared. And that is 1/10 of 36 minus 1. And that is 1/10 of 35. And that is 3.5 still, right? It totally matches what we were doing before right there, even with that somewhat odd statement that the probability distribution function is a height of 1/5. It still panned out to be the exact same value. We still have our expected value being exactly halfway between 1 and 6 right there. So to do our continuous analog for this guy, we just rewrote our sum as an integral and moved on. And that was all that really happened right there. So I want to make a couple statements about our probability distribution function before we move on to writing it, doing our next example right here. So here's the important thing that's different about this guy, right? That we want to be a little bit technical about. And this is actually a thing where I don't ever need you to directly use this in this class, but I just want to show you a really cool idea. That I remember when somebody showed me this, I was like, holy crap, that's like the best notation I've ever seen for something. So what I'm going to say here is that this is sort of a misleading statement because this says to me f of x equals 1/5. That to me is a horizontal line forever. And I really just want to say it's only when x is between 1 and 6 right there. So a more appropriate way to write this then would be that f of x is, the probability is 1/5. The height of our function is 1/5 when 1 is less than or equal to x is less than or equal to 6. And the probability is 0 otherwise, right, in all other places out there. Because there is no probability that our computer will ever output the value of like 14, right? It's never going to do that. It's always going to be between 1 and 6. So kind of the annoying thing here is that most all continuous probability distribution functions, or I shouldn't say most all, but if the distribution isn't explicit, like if the function of interest isn't to be used for all x values from negative infinity to positive infinity, then you really need to be referencing the chunk at which the probability is 0 of it occurring, right? If you only expect positives to be taken in, then you would say, oh, it's this function for x greater than 0, and it's 0 for all the negatives out there, or something like that. So the annoyance here is that in most statistical cases, you have to write a piecewise function for every PDF to indicate where it's defined and where it's not defined. This is just us saying only use this PDF over the interval from 1 to 6, 0 everywhere else. It's a really easy idea. It's kind of a pain in the ass for notation. So here's the very cool thing that I was shown. This is just a little piece of notation right here, but I really like this notation as far as eliminating, to eliminate piecewise notation. We define an indicator function. Man, I needed a lot more room than I thought I did right here. So what is an indicator function? An indicator function just tells you when things are 1 and when things are 0. An indicator function, for us, we're going to say that the indicator function for the variable x, and down here we'll give an interval. So maybe I'll notate it like this. I of x, where x is an element of the open interval from a to the closed end point of b, is going to be 1. It's going to be 1 if a is less than x is less than or equal to b. I'm just writing a general example with the parenthesis in the bracket there. And it's going to be 0 otherwise. So this is a light switch function. It's on if your x is in the bounds it's supposed to be. It's off if x is not in the bounds it's supposed to be. And what this allows us to do then is we can then update our PDF to be written as not as a whole piecewise function. I'll let the piecewise be contained within my indicator function. So this is maybe my more formal representation of my probability distribution function here. Because notice, this f of x, if you plug in 8 for x, then I'm going to get 1/5 times I of 8. I of 8 for us will be 0, because 8 is not a possible outcome. It's not in our interval of interest. And therefore, 1/5 times 0 is going to give us 0 for the probability. On the other hand, if you ask me what's f of 2, then I'm going to plug in 2 into this function. I'm going to see that 2 is in our bounds of interest, so I'm going to get 1 from my indicator. So that just says, okay, just keep the 1/5 component. So this is literally just a light switch function. This just turns on and turns off whatever it's multiplying by. You're either multiplying by 1, meaning leave it alone, or you're multiplying by 0, which means make everything go to 0. So indicator functions are piecewise functions. But if we all just understand that an indicator function only ever outputs 1 or 0, then we never need to like explain it. And then this is now a way to write a piecewise function without literally writing the piecewise stuff, because the piecewise component is trapped up in the indicator function right there. So indicator functions are a really handy dandy way for you to never actually have to write these boring piecewises where it's just, oh, and 0 otherwise, 0 outside of the bounds of interest. Like, that's just an obnoxious notational thing to have to do, and that turns out to be a lot more convenient. And then it turns out you can even like do math with your indicator functions out there. There's a sensible quantity that we're now multiplying by. So that's just a little bit of cool statistical notation that's out there. I really like the idea of an indicator function that is literally just an on-off function. It's either you get that part or you don't, depending on if your x value is within certain boundaries or not. So indicator functions, pretty cool. Okay, so where are we at here? So in general, we expect the expected value of any probability distribution function f of x to be given by, if we're discrete, then expected value of the variable x is given by the sum of the f of x sub I times x sub I. And if we are continuous, which is much more typically our case in this class, since we're here to talk about calculus stuff, then we're going to be getting the integral of x, f of x dx. And it matters that we, I'm just going to put right here bounds. It matters that we identify what our bounds of integration are on these guys right here. This is referred to, I guess, more things to talk about up here. When we talk about this like 1 to 6, we say that the support of this function, stats we say, so this bounds of interest is referred to as the support. I don't know why. That's just a word right there. And again, I'm going to give you guys way more vocab than I care for you to like legitimately like carry with you and stuff. But that's just because we're here to get our flavor of probability and statistics for today. So I feel like I might as well use all the words that are actually used out there. So the support of a PDF is the bounds over which it's not equal to 0. It's where it's defined. So we've got our statements here for expected value. So let's do something a little bit more interesting here, and let's talk about building our own PDFs, finding probabilities given a PDF, and finding some very important values of location, mean, median, and mode associated with each of these guys right here. So Mean, median, mode, I mean huge things in probability and statistics. What we're going to see here is that these are all calculus defined quantities here. So here's my situation. And by the way, what I'm very much trying to do for you right here in this example, and especially example, the question number one, is trying to help you think about our take-home homework question for this week right here. So I'm trying to like allude to that here. Suppose we'd like to build a continuous probability distribution function. We're going to call it f of x. We want it to have support over the interval -2 to 4, meaning the probability is 0 that we will see any outcome outside of -2 to 4. -2 to 4 is where we have non-zero probability. We want this function to have a minimum probability when x is 0. We want it to have a maximum at of when x is at 4. And we want this function to grow quadratically from x equals 0 to x equals 4 and from x equals 0 to x equals -2. So I'm basically saying this is going to be a quadratic function here. What I would like to know from you is, what is the probability distribution function? How can we determine that information? If we can determine what the PDF is, then we can determine what is the probability that we would see an event x that is between -1 and +2, things like that. And then we can talk about computing some statistics of interest relative to this probability distribution function, mean, median, and mode. So let's kind of do, I listed all three of these here, but let's kind of do these obviously one at a time right here. So what I'm kind of thinking to myself, I want to like think about what was described to me. And by the way, again, thinking towards the by hand homework for this week, draw a picture for yourself, like just sketch some stuff out. All right, so for problem number one here, what is the PDF? I've been told a couple things, right? So a couple things I know is my probabilities are always positive. So as I'm graphing PDFs, I never need the bottom of my graph because I'm never going to have a negative probability ever. What I know is I expect this thing to have a minimum at x equals 0, a maximum at x equals 4, and it should grow quadratically. Let me slightly change this. I don't think I was quite descriptive enough right here. Let's just do this. There we go. That's what I wanted to say. A minimum of f of 0 equals 0, right? That's saying to me, if you plug in x equals 0, there is actually a 0 probability of that occurring. So I know that's a point on my graph. I know that this graph is going to vary quadratically. That's what I've been given. It's going to grow quadratically both from 0 to 4 and from 0 to -2. And so I am expecting here that if I give myself some tick marks out here, that there might be some values out here describing a quadratic of interest right here. So this is what I'm picturing for my probability distribution function. Now the important thing is I haven't identified any of my y values. I've only identified some x values here. What I am really partly interested in knowing is like, what function is this actually? Like I want to know, what is f of x right here? So here's what I know. If a quadratic is centered on the y-axis, so I'm thinking this should in general be like f of x equals ax squared plus bx plus c. But what I know is we're centered on the y-axis. That's going to tell me that b is equal to 0. And the fact that our y-intercept is 0 is going to tell me that c is equal to 0. So what I'm looking at for myself right now is I know that this, whatever my probability distribution function is, it should be ax squared, and that should only be defined over the interval from -2 to 4 right there. Right? So there's my, I know sort of what my PDF is. It's ax squared, whatever a is, but it's only supported from -2 to 4. All right. So here's what I'm thinking to myself. I need to know what a is, or else I can't compute any probabilities here. I don't have a probability distribution function until I know what a is. How can I find what a must be? Well, I'm going to go back up and I'm going to say, well, I don't know how our probability distribution function is defined. And what we have agreed on is that the sum of all the probabilities is 1. Therefore, the area underneath my probability distribution function needs to be equal to 1. That's exactly what we did right here. The area underneath the PDF must be equal to 1, always. If it's not, then it's not a probability distribution function, period. Every single probability distribution function that there is, the area underneath the entirety of the curve is 1, always. So we can take that to the bank down here. let's go ahead and say that the area underneath this curve needs to be equal to 1. So for f of x to be a probability distribution function, we need that the area underneath the whole thing to be equal to 1. Right? That would say that all 100% of all probabilities have been accumulated. So we can go ahead and do that here. So I'm thinking to myself, integral from -2 to 4 of ax squared dx equals 1. Two things. One, that a is just a constant that I can pull out front. Second, the integral of x squared is super easy. It's going to be 1/3 x cubed. We're going to evaluate this from x equals -2 to x equals 4. And we're claiming that this should be equal to 1. The fact that we know it's equal to 1 is what's going to allow us to solve for what a must be. So it looks like here we can say that a times, and what are we getting here? We're getting 1/3 of 4 cubed, that's 64, minus 1/3 of -2 cubed, that's -8, should be equal to 1. That's a times 64 thirds plus 8 thirds equals 1. That's 72 thirds. And 72 thirds, actually, no, that's 20, wait. Right? No, that's 20, wait. I can't do mental math in my head all of a sudden. What's going on? 72 divided by 3 is 24. That's right. I was going to say 27. I was like, that's not right. So it looks like A is going to be just 1 over 24. Right? This is 24 over 1. I just divided 24 to the other side. So I'm getting A as 1/24. So what this says to me is our PDF is, really get rid of that stuff. So it looks like our answer to number 1 is our PDF is f of x equals 1/24 x squared. And that is only defined, we'll use our indicator function to say it's only defined from -2 to 4. Right? So we found our PDF. That's good. I now know what curve represents the probabilities of interest for me right here. And I know that this is a probability distribution function because I just guaranteed that the area under this curve from -2 to 4 is 1, saying 100% of all outcomes have been accounted for. Next up, I'm interested in determining the probability that our x value, if we were to randomly select an x value from this distribution, what is the probability that it will be between -1 and 2? Right? There's just a probability statement right here. Now, let's go ahead and estimate this real quick here. Do we think we're going to need a lot of probability or a little bit of probability? We're looking at between -1 and +2. So between -1 and +2, the thing that I'm seeing here is that between -1 and +2 is very much the lower parts of our graph. What I'm seeing here is the probability of seeing events like between 3 and 4. This amount of area right here is a large amount of area, so it's a large amount of probability. I'm seeing that this is a pretty small sliver of probability right here. Between -1 and 2, we're very, very low on our graph right there. So I'm expecting to get a relatively small answer here. Something maybe in the ballpark of like 10% or something like that. I'm really just asking myself the question, what proportion of all of the area from -2 to 4 is the proportion that's between -1 and 2? And here it looks like a pretty small chunk. Again, from 2 to 4 looks like most of it out there. That's probably more than half between 2 and 4. I'm expecting a pretty small chunk between -1 and 2. So again, I don't know, vaguely estimating something like 10%. Right? And again, remember, we're looking at this guy going from -2 to 4, and we are interested in this span right here from -1 to 2. And so we're interested in this area. That's what we're trying to accumulate right here. That will be equal to our probability. So doing this isn't really too bad right here. I just want to make my estimate before I do it. To determine this probability, it's going to be real easy for us here. We're just going to integrate from -1 to 2. The probability is equal to the area under the curve, and that's great news for the fact that you know integration. So I'm going to take my 1/24 x squared. That's my probability distribution function. We're not looking for expected value, by the way. There is no times x in here. We multiply the PDF times x and integrate if we're looking for the expected value. Here I'm trying to compute a probability. So the probability is equal to the area underneath the curve. Area underneath the curve is just the integral of the curve, and the curve is the PDF. So I've just got the integral of the PDF right here. So this should be 1/24 times 1/3 x cubed evaluated from x equals -1 to x equals 2. I might suck this 1/3 back out right there to get back to my 1/72 that we'd seen before. And then this should be 2 cubed is 8 minus -1, right? That 2 cubed is 8, -1 cubed is -1. So that looks like it's 1/72 times 9, and that's going to give me 1/8 right there. And that's actually pretty dang good because that's actually 0.125, which says this is actually a 12.5% chance. Right? That's the probability of us drawing something between -1 and 2 with this distribution function right here. So my guess was super good right there. That 10%, I'm actually pretty pumped about that. I did not actually compute this number before this lecture right here, so I feel excellent about that guess that I made right there. Make guesses. They make you feel good all the time. So there we go. So computing probabilities is super easy. If you know the PDF, just integrate over the bounds over which we're interested in, and then that's all you're doing. It's just a direct integral right there. Nothing weird just happened right there. So problem 3 is, I think, a little bit more of an interesting question here for us. Let me copy it and bring it down. This one I really like. I really like talking about how our simple statistics, generally simple statistics, are mean, median, mode, standard deviation, maybe quartiles. Even quartiles get a little less simple right there. So what is the mean, the median, and the mode of this distribution right here? Well, let's talk about what each of these mean in general. The mean is our average value. Right? So the cool thing about computing the mean here is that this should literally just be the same thing as our expected value that's associated with this guy here. And so we can just go ahead and do our expected value computation here. So to get the mean of this distribution, I'm going to compute 1/24 x squared times x dx. This is our now expected value. I'm going to do this over the entire support from -2 to 4. So it looks like this is going to be 1/24. This is really x cubed, so I'm going to get a 1/4 x to the 4th. And I'll evaluate that from x equals -2 to x equals 4. 1/24, that's going to be a 1/96. 4 to the 4th is what? 256. Minus 2 to the 4th is 16. And notice -2 to an even power is positive. So what's that, 240/96? And so that tells me, when I do this 240/96 right here, oh, that's just 2.5. Interesting. That came out nice and easy right there. So what this says to me is, if you were going to draw lots and lots and lots and lots and lots of samples from this probability distribution function, on average, the most likely outcome for you to see is a 2.5 right there. That would be a long-term average outcome that we're going to experience right there. We can always find expected value as the PDF. Maybe I should just write this over here. Expected value of x is the integral of f of x times x dx right there. So we found the expected value of this function here. So there's our mean. How do we find a median? A median is going to be sort of related to this guy right here in a sense. They're both measures of center. A median is an x location It's an x location where half of the outcomes are to the left and half of the outcomes are to the right. Right? And real quick, just for our mean and for our median example, real quick here. If I gave you the numbers 1, 2, 3, 4, and 5, We can compute the mean of this distribution. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, divided by 5 values. That's 3. We could also compute the median of these set of 5 values here. I typically do this by just like kind of working my way from the outside to the inside since it's an ordered list. And it looks like 3 is going to be the median value here. Now I'm going to alter this real quick here and say 1, 2, 3, 4, 50. Now when I go to look for the mean of this set of values, I'm going to get 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 50 is 60. 60 divided by 5 values is 12. When I go to look for the median, I'm going to do the same move, and I'm going to sort of cross off from the outside to the inside since it's an ordered list. And it looks like the median here is still 3. So realize that averages are sometimes terrible descriptors of the center of our data because averages are heavily influenced by outliers. So it's often the case that if you have a very skewed distribution where you have outliers, it's typically better to use the median rather than the mean to describe that data. That's the reason why, for example, average home price is all. I just said the wrong words right there. Home prices are generally described by their median value rather than their mean value. Because if one, like, if you live in the same neighborhood as Bill Gates, well, guess what? His home costs like $100 million. So it's going to wildly drag up the average, but it won't basically have any impact on the median right there. If people are telling you the mean of a skewed data set, then they are trying to mislead you. A statistic that I have heard more than once is that average home prices in San Francisco are the highest of anywhere in the entire world. That's true, but that's also a misleading statement because average is a terrible descriptor of home prices because it's a heavily right skewed distribution. Median home prices in San Francisco are still really high, but as far as like world rankings for big cities go, it's like 8th or ninth instead of number 1 because average is just a terrible descriptor for home prices because it's not a symmetric distribution. So anyway, there's our median. So median is where half the stuff is to the left and half the stuff is to the right. So how are we going to compute where a median might be? So let's picture a different distribution here. Maybe if we had a distribution that looks very right skewed like this guy does, a long right tail, what we are interested in locating is where the median, which by the way is typically denoted with a capital M, wherever the median is where this should be half and where this should be half. So it looks like to find the median, we are going to want to accumulate all of the area up to some certain location. And that should get us half of all the outcomes, meaning half of them are to the left of that location, half of them are to the right of that location. So the median is defined with an integral quantity for all continuous random variables out there, right? If you're talking about a continuous distribution out there, the median can only really be known with an integral, which I find to be hilarious because in all other settings, we really only talk about the median of discrete functions whenever we're in a stats class, but continuous functions can have medians too. It's where you've accumulated half of all of the outcomes out there. And I accumulate area as I accumulate probability. Those are the same. We want to accumulate half the probability to say that we're at the halfway point, the median point out there. So if I want to compute the median location of our distribution, then I can set up my integral here. And by the way, this is just my generic lower bound right here. I'm going to throw back in our -2 here in a second. So we can go ahead and do our -2 up to some unknown median value up there. I don't know how high up I need to go, but I do know that I would like for my total accumulation to be half of all the associated probability out there. So this is, in a sense, a little bit similar to when we did before when we didn't know that 1/24th, but we knew the whole thing was equal to 1. We can solve for the parameters or statistics of interest by often setting an integral equal to what its known output should be here. So what am I getting here? This should be a 1. Oh, I kind of wrote that. Uh-oh. Okay, cool, cool. So I'm going to write this as 1/24th integral from -2 to the unknown median of f of x here. Oh my gosh, I see. Okay, all right. Let me just. All right, whatever. Give me the thing I was trying to write. All right, let's start over again with that stupid writing, and then we'll talk about our normal distribution and call it a day. Seriously? Oh, come on. Why are you doing this to me? I don't know why you do this. Escape. zooming. I don't want to zoom. Stop doing this. This isn't what I'm trying to do. Why are you highlighting these? What's going on here? I can't believe this. I'm not trying to select anything. I'm not selecting. I'm not selecting. Can't press escape. Oh my God. How is this? What did I even do? Oh my gosh. Oh, I have such high hopes for this computer that's in the mail. Okay, I'm going to come back to this problem that we were on a couple minutes ago now. I want to find the median. The median should be the upper bound where we've accumulated half of all the area to the left of that upper bound. Our distribution function was 1/24 x squared dx, and I want this to be 1/2 of the area that I've accumulated up to the median. This should be giving us 1/24 times 1/3 x cubed, evaluated from x equals -2 to x equals m, equals 1/2. So let's go ahead and do some maths here. Here's some quick things I'm seeing. 1/24 times 1/3 is 1/72. I'm going to multiply both sides by 72 to give me a 36 here on the right. All right. So again, 1/3 of 1/24 is 1/72. Multiply 1/72 to both sides gives you a 36 on the right, and I've dealt with all the fractions. The upper bound is m, so I'm going to get m cubed minus -2 cubed here. So that's going to be m cubed. It looks like this will be a +8 equals 36. It looks like our median is going to be the cube root of 28. And if I do the cube root of 28 right here, 28 to the power of 1 divided by 3, and 3.037. All right, and so we've now computed the median here. We can see the median is a bit different than the mean, and what that's telling me is that we probably don't have a symmetric distribution. When the mean and median match, that's our good indicator that we have a symmetric distribution. We got a median of 2.5 and a mean of a bit over 3 right there, but that's okay. We can tell that this isn't a very symmetric distribution, right? This has a lot more going on the right than it has on the left. So I wasn't expecting necessarily to get a mean that was equal to the median. Cool. So we've accumulated half of all of our area up to that 3 value right there. And now I know where the median is located of my distribution. Finally, we're looking for the mode. The mode of a distribution is the most common outcome. So if we're looking at, for example, a bunch of outputs like this, I think it's likely going to be the case here that 2 is the mode, right? I typed it out like that here. Right? It's just the most common thing that we see. What you should sort of be picturing for yourself out here is it would be the case that if we were going to make like a histogram for this thing, 2s, 3s, 4s, and 5s, we had a whole lot of 2s. We had a lot of 3s. We had very few 4s and like 2 5s out there, right? If I were to make a histogram for this data that I just listed right here, we can see that 2 is the tallest bar, and that's how I know it's the mode. So that's going to make things really, really easy for us over here with our PDF. We are looking at a PDF that looks like this. And so I can see here that x equals 4 is my highest probability event of occurring. Right? So the mode of this distribution would be 4. Now, what you should be asking yourself is, where's the calculus happening here? Well, what were to happen if we were to flip this guy? All right, so what if we got something that wasn't, I don't know, concave up and was instead more like concave down here? Then you should identify that visually the mode is right here. But how are we going to find that location? Fortunately, you've taken calculus, so you know exactly how to find that location. So what I would like to do now is sort of bring this back to kind of wrap up today with what is our most important distribution in all of statistics, which is the normal distribution. By the way, did I finish answering this question? Mean, median, and mode of the distribution. Okay, we got the mean is the expected value. The median is where we've accumulated half of all the probability. The mode is always going to be the highest point that we experience here. It's the maximum over an interval. You discussed maximums over a closed interval last semester in Calc 1. What you determined is it's either at your critical locations where the derivative is equal to 0, or it's one of your endpoints. That's exactly what we covered in Calc 1, is that the maximum value over a closed interval is either where the derivative is equal to 0, or it's at either A or B, your lower or upper bound. In this case, it would be at B. In this case, it would be at a location where the derivative is equal to 0. So let's talk about that in the context of the normal distribution here. So the normal distribution, I thought I had a line under this. Now is that stuff gone as well here, I'm assuming? The normal distribution is defined by this horrendous looking function here. I know I've brought this up multiple times this semester, so let's just state a couple quick things about the normal distribution and why do we care about still talking about calculus related to this. So there's 3 different calculus statements that I want to make here. One, we cannot integrate this function. Right? So what we saw today is if I wanted to compute, for example, the probability that my son will grow up to be between 6 foot tall and 6'1", I would use a normal distribution since heights follow a normal distribution with the average height being 68 inches and the standard deviation of height being 2.5 inches. I would compute the integral from negative infinity up to 70 inches, where it's 6 feet tall, right up there. Okay, that would give me my probability that it's going to be under 6 foot tall, 6 foot tall or shorter, right? But I can't do that integral. Because it's not integrable. It's not an integrable function. That's hugely disappointing since all probabilities are integrals of the probability distribution function, right? Now, as I have shouted at you a couple times, it is actually possible with some multivariable calculus techniques to make this happen, but we have to sort of expand this into a 3D scenario, compute the integral in 3D, and then re-extract just our 2D information from it again. In 3D, this is a doable integral, and in 2D, it's not, which I just think, even if there wasn't practical applications to that, is incredibly interesting. But in any event, you'll see that in 50C next semester. So that's the kind of one calculus statement I want to make here, is that this is not an integrable function, because this is essentially, right, if you just wash away all the constants here, or I should say, if we let, well, whatever, this is about e to the negative x squared, right? That's about what we're looking at right there, and that's just not integrable, which is highly unfortunate for all of statistics. So what that means is every single normal distribution probability that's ever been calculated was calculated using something like the trapezoid rule or Simpson's rule applied to this integral setup right here. That's just how your calculator is doing things. When your calculator is not extrapolating into a 3D scenario and then recondensing back down to a 2D scenario, your calculator is just using Simpson's rule on this function right here to estimate all probabilities, because we can't integrate this thing. So what other special calculus statements can we make here? Well, another thing I know about this function is that this thing follows a bell-shaped curve, right? That's our normal distribution. Even if you haven't taken stats and don't know about these things here, I expect that everybody's got some vague sense of our bell-shaped curve out here. And what we might be interested in identifying is what really are this mu and sigma here, right? So let me just say here, mu equals the average, and sigma equals the standard deviation. Well, what do I mean when I say how are they really defined out there? Check out some really nice things that happen here. If I take the derivative of this function right here, okay, here we go. I'm going to take a derivative. And what I see is that this is an e to the negative x squared. So what I know is I'm going to get back the entire, 1 over sigma root 2 pi. I'm going to get back the e to the negative 1/2 x minus mu over sigma squared, right? But what I'm going to have to multiply by is the derivative of the inside function, right? And the derivative of this inside function, we can see here, the 2 is going to pop down to just give us a -1, right? Because this is really just some quadratic that's in here. And then times the derivative of that inside function, which is just 1, right? So it looks like what I'm going to be getting here is negative. The 1/2 and the 2 cancel, and I'm just going to get x minus mu over sigma. Now notice if I set this equal to 0, what does this give me? Where is the derivative equal to 0? Well, this gives no roots. So no place where the derivative is equal to 0. And this phrase is going to tell me, oh, the average is where mu is located right there, right? So how is this defined in terms of calculus things? The average, mu, is exactly where where our derivative is equal to 0. Now, what I'm not going to do right now, because it's a giant pain, is I'm going to show you the next thing associated with this graph right here. So if we look at A, and in fact, is this worth drawing up a... No. Okay, I actually am going to do that here. If we go look at, I'm going to grab an image real quick right here. So very typical thing to see in our normal distribution. Here's a perfect picture right here. Actually, I even want this one right here instead. All right. So, oh my gosh, just what's happening here to me today? So here is a much nicer bell-shaped curve for us. And here's the question that I want to ask. Where is sigma? How would you really find where sigma is going to be located, or one standard deviation away? Well, where is one standard deviation away? And my question to you is, if I'm going to mark these 2 points on a graph and say to you, hey, what special calculus stuff is happening on this graph? Clearly, we can see that the average, the x value of the average, is right where the derivative is equal to 0. Then you should be looking at this guy, and I'm asking you the exact same question. What special calculus idea is representative of what's happening at this dot? And this is a little bit harder one to see right here, but here's what you should be able to see. The middle chunk of our normal distribution is concave down, right? And hopefully you agree with that at this region up here at the top, that we are concave down up here. But what you can also see out on the edges is that we are concave up out on the edges out here. We are bowed up along the edges. Where is it that we make our transition from being concave down to concave up? Is right here at the inflection point. It turns out that exactly mu plus sigma, one standard deviation away, above and below, are exactly the inflection points that are associated with the normal curve. So mu plus sigma, that's where f double prime of x is equal to 0. right? So the really cool thing about all of our normal distribution quantities, the average is where the first derivative is zero of our distribution function, and the standard deviation is where the second derivative is equal to zero. It's our inflection point. It's exactly where we change from being concave down to being concave up on this function right here. So this is always a question I put on like my Calc 1 tests and stuff like that. Is like, tell me where the second derivative is equal to zero. And we end up finding, I'm not going to do it because it's kind of an algebraic pain in the ass, as you can imagine right here. But if you were to take a second derivative, you should be finding that mu plus sigma is exactly the x value that you get when you take the second derivative and set it equal to zero right here, which is just a really interesting idea. So it's cool to see that mean, median, mode, and standard deviation, at least of a normal distribution, are all explicitly calculus defined operations here based on integrals and based on derivatives here. And so this is sort of the conclusion as to why is it so hard for Tony to teach statistics and when he's teaching calc at the same time? And it's because all I want to do with these people is take derivatives and integrals to show them where things are happening, and I can't. And I literally get students that are like, how can you tell like where one standard deviation is away? And I'm like, I have an excellent answer for you, and I can't tell you any of it until you've taken like 2 more semesters of math, unfortunately. And I hate that when people ask me great questions that are exactly what they should be asking, I don't have the route to tell them what to do because they don't have the prerequisite knowledge to understand the answer right there. But it's very cool to see that like all probability and statistics computations all boil down to being integrals and derivatives, which is just not obvious because it's incredibly rare in the US that anybody takes a probability course that is based on calculus, calc-based probability. And so I'm going to wrap up this video by giving this as my pitch to you guys. And with a brief stupid Tony story here. When I was graduating from undergrad, I had transferred partway through my degree, as many of you will end up doing. I did 5 semesters at St. Louis University and 5 semesters at Western State College. I did a stupid thing, and that's when you transfer, you need to be really careful about where your credits end up going and what they end up getting counted for. And I transferred some of my credits in as different classes than I actually took them as. They did a course substitution for me where they said, well, for this degree, you're really required to take this class, but you took this extra class that we don't offer at our school when you were at your previous school. So we're just going to count the class that you need here as that one different class you had before because it's essentially serving the same purpose of like advancing your math degree kind of thing like that, right? So I did some course swaps like that to help fill in some of the gaps in my transcript, but I kind of did not track those super carefully. And so what ended up happening to me is in my 5th year, as I was getting ready to graduate, as I was filling out my application to graduate with my bachelor's, I was counting up all of my credits and I realized that we had copied over one course from St. Louis to Colorado, but we didn't sort of subtract those credits. We sort of double counted it is basically what happened. I counted it as its actual class and as the class that we substituted it in for. And so what I ended up discovering was I actually only had 29 upper division credits when I was required to have 30 upper division credits to graduate. And so this is me sitting there with the head of the math department was my advisor. I'm sitting there in the office with him. He's the one that signed off on my sheet 3 semesters before approving of my like plan to graduate in a year and a half kind of thing. And so he and I were both sitting there being like, crap. And he was like, okay, he's like, technically this is your fault since you need to be on top of this, but technically I signed this document, 3 semesters ago that approved of this plan. So this is also technically a bit my fault right here. And he said, here's what we're going to do. You are missing a credit, so you can't graduate. He said, so what I'm going to do is I'm going to create a new math class so that you can have 1 credit of math class to take as an upper division credit. We're going to offer that class next semester. You're going to take it next semester, and you're going to graduate next semester, and we're all going to be good. And I said, okay, great. And he said, okay. He's like, tell me what class you want to take. We'll just make a class around that. And I said, I don't know. How about some like probability stuff? And I don't even know what caused me to actually want to do that right there. I think I had just seen an interesting talk recently where somebody computed the probability I didn't know, and I was like, I don't know, how about this? And so he said, perfect. We'll be offering a 300 level probability and statistics course next semester that's based on calculus, and you're going to take it, register for it immediately, and then we'll all be good with your graduation. So that ended up being the last 1 credit I needed to graduate. It ended up being a super cool, interesting class. That really has kind of like led me down this path of finding probability and statistics questions to be some of my favorite kind of branch of math that's out there. And now that college that I graduated from, they now have an entire emphasis for the math major that is based on this probability and statistics class now. They now have a data analysis class or emphasis that grew out of this calc-based probability and statistics, and an actuarial emphasis that also came out of this also. So they actually this actually provided a lot to their program by me being in this pickle and them just providing me a 1 credit 300 level class. So if you have the opportunity, so this story is to say, if you have the opportunity to take a calculus-based probability and statistics course, I would strongly encourage you to do that. I think it was one of the coolest classes I ever took as an undergrad, aside from the fact that it totally saved me from a screw up that I did. Very, very interesting stuff. I know that lots of like mathier people, lots of STEM type students end up taking statistics and they end up not liking it because every statistics course is aimed at people that are basically like barely getting through college algebra, right? The non-STEM students are who are taking stats. The STEM students are taking calculus. So often what happens is the people that are just better at math take stats and they don't like it because in stats we have to sort of hand wave over a lot of the underlying stuff that's going on because it's all calculus based. What that means to you is don't allow yourself to think that you don't like probability and statistics. You have seen the version of it that we teach to people that can't understand where most of the computation comes from. You should go and take a 300 or 400 level probability and statistics course, and I can't guarantee it, but I can tell you with a high level of confidence, there's my probability statement, that it's way more satisfactory than taking an introductory stats course where it's like if you don't have your calculator, you can't compute anything and no calculus is taught in the class. So do that. Even if it doesn't count towards your degree, take a calc-based probability and statistics class at some time. It was fascinating. One of my favorite, and obviously I love all the math classes I take. Even the ones that I fail, I say that I've loved for sure. And I crushed this one, and it was super cool. So I'd highly recommend that. So that wraps it up for me here today. You should be confident in your ability to manage probability distribution functions. Since the area underneath a PDF is 1, you should be able to construct PDFs. You should be able to compute probabilities given a PDF. You should be able to find means and medians and modes because all of those are calculus-defined quantities out there. And I gave you a very cool little probability project that I gave to myself over the summer in your take-home homework there. So I really like that question in there. I really like the idea of sort of forming a probability distribution based on verbal information, sort of like we did up above there. Mine is a more thought out one in the homework than we saw above right there. So do that. Email me all your questions. That is it for us this week. Maybe my final statement to say is if you're looking up above my head here, you should see that we're wrapping up Chapter 8 this week. We're not covering Chapter 9 because that's differential equations. You're just going to take that class with me next semester. That's Math 55. We're going to start Chapter 10 next week, which is going to be a wild diversion from what we've been doing. We're going to talk about parametric functions that are defined x of t and y of t, two parameters x and y that are both based on a single parameter t. And then we'll look at applying some calculus operations to parametrically defined curves out there. Parametric curves are very useful because they don't have to represent functions in the traditional sense that we think of a function as being passing the vertical line test. Parametric curves are easy ways for us to define useful and obviously useful functions that perhaps loop over on themselves or something like that, are not passing the vertical line test, but are still representative of scenarios that we want to describe out there. So parametric stuff and polar coordinates are what's coming up in Chapter 10. And that's what we'll be starting on next week here. So I will see you guys for that one. Have a good one.